Okay, guys, let's continue with part 2 of lecture 4. Okay, so this is example 4.1. We have the basic configuration used in tripping circuit breaker. Okay, when you want to break a circuit, an electric circuit, and we can use a circuit breaker to do that. And we won't do that by hand. We will apply a current through a coil, and that coil can move this part. So this one is moving up and down. This is the sleeve going round here, and it's a non-magnetic one. So inside that sleeve, the permeability will be just like the air or the vacuum. Okay, so we have a coil here with n turns. In this structure, we can identify two paths: path 1 here and path 2 here. Okay, so in the live stream, I'll explain in more detail, but here you can see that we apply the Gauss law. Okay, so we can prove that H1 equal H2, and then we can calculate the flux linkage. And in this example, we need to find H1, H2 lambda flux linkage, and the final one is the induced voltage. So after you find the flux linkage, you can calculate d lambda by dt to get the induced voltage. And here's the very simplified of a rotational system. So in this structure, the rotor here is rotating like this or like this, and this stator is stationary, it's not moving, it's attached to the ground, for example. Okay, so we have two coils, one on the rotor which we supply current IR, and we will have VR and lambda R associated with that coil. And here we are on the rotor, on the stator side, we will have another coil, and we supply the current IS, and we will have the induced voltage VS and the associated lambda S. Okay, so in the live stream session, I will explain more. I will go through a more detailed calculation. Okay, so basically we can find out that the HR1 is equal HR3 in magnitude, but they have a opposite direction. Okay, and HR2 and HR4 will have a similar, we have the same relation. Okay, so we can calculate the total flux linkage on the stator side lambda S to be like this, and then we can find the flux linkage on the rotor coil. In practical machine, we can calculate, we will manufacture so that the lambda S will be a sinusoidal function over the space when you go around the air gap in the machine. Okay, the flux linkage will vary as a sine function. So it's a sine function with respect to time, and a sine function with respect to space as well. It's a sinusoidal with respect to time, because your current IS here is a sinusoidal function, time function. Okay, so this component is sinusoidal with respect to time, and when you have proper air gap, then at a steady state, at a steady speed, at a constant speed, the sinusoidal variation in space will convert it into a sinusoidal variation in time. Okay, so let's have a look at an electromagnet. So here, this part can move up and down. Okay, and this part with two coils will be fixed. Okay, ohm will have the width of W. This coil will have N1 turn and current I1. This coil will have N2 turn and current I2 with the direction as shown on the picture. So we will need to find the force. Okay. But before we can do that, we need to we might try to find the induced voltage in both coil when the moving part here can go up and down. Remember, in our course here we only look at structure with just one moving part. Okay, so we can establish an equivalent magnetic equivalent circuit as shown on the screen here, and after some calculation we can solve for phi1 as the function of I1 and I2, also phi2 as a function of I1 and I2, so we can calculate lambda 1 and lambda 2 as we normally do. And therefore my question is, can we identify the cell and in mutual induction now? So that is the end of part 2.